All right, we are heading into 8.1, which talks about the sine law. So last unit, you learned the tools that you can use in order to solve triangles that are right angle triangles. This time we're going to learn a couple of tricks in solving triangles that do not have a right angle. One of those tricks, one of those tools is to apply the sine law. I'm just going to quickly show where this comes from, how we can use it, the reason why we're allowed to use it, why it makes sense. Okay, so here is my triangle. This is triangle A, B, C, and this is not a right triangle. Okay, this is not a right triangle. It has side lengths that measure C. Opposite here is lowercase a, and opposite here is lowercase b. So I've just named all the sides and vertices in my triangle. And again, I'm just going to demonstrate why we can use the sine law, okay? And then I'll give you a definition of the sine law and write down the actual law. I'm going to take this non-right triangle, okay? And I'm going to put the altitude in there. And now what have I created? I've actually created two right angle triangles. I'm going to call this point X so that we can talk about our two triangles. Okay. Now, what do you know about these two triangles? Do they have anything in common? Yeah, just like we did an example a little while ago, they share the height. Okay, so we're actually going to use the same concept of the idea that we're going to get an expression for h from both triangles, and that's going to help us to develop the sine law. Okay, so first we're going to, yes, you should definitely be writing this. So first we're going to look at triangle AXC. That's this piece on the right hand side here. Okay, and we're going to come up with a primary trig ratio because we're in a right angle triangle, and we're going to use just what we see here. Okay, so really the only side lengths that we have labeled are B and H. B and H. Okay, so if we're looking from A and we have opposite and hypotenuse, we're looking at using the sine ratio. Okay, so I'm developing a sine ratio from angle A. So we've got the sine of A is equal to opposite over hypotenuse is equal to H over B. How do I get an expression? How do I rearrange this equation to get an expression for H? I want to isolate H. So I'm going to multiply both sides by B. That's going to give me H equals B times the sine of A. All right, that's helpful. Let's go over to triangle BXC, triangle BXC. And we're going to do the same thing. We're going to look from angle B here. And we have opposite is H, hypotenuse is A. So our sine ratio becomes the sine of B equals H over A, opposite over hypotenuse. Rearrange that in terms of H. We're going to multiply both sides by A. I end up with H equals A times the sine of B. We're all good so far? All we did was we developed two different expressions, two different equations for H. One of them from the triangle on the right-hand side, A times the sine of B will get us the height of this triangle. And also from the left-hand triangle, we can get the height using B times the sine of A. Okay, well, what do we know about these expressions if they both equal H?
You can conjoin them.
So I can't conjoin them, but what does it tell me about this side and this side?
They're equal.
They are also equal. They both equal H. H must equal H. That's what equal signs do. And so we can say safely that B, and if you want to do like a little therefore to help you realize that you're now taking this information and combining it into a new kind of thought here, B times the sine of A is then equal to A times the sine of B. And again, I just drew a random triangle acute triangle. It doesn't have any obtuse angles, but it's just a triangle. I can do this with any triangle. I could break it into 2 right angle triangles, okay? So this will work across the board no matter what your triangle looks like. Well, let's come up with an expression for B then. So what we're going to do here is divide both sides by the sine of A. Okay, so we're going to take this, divide the left side by the sine of A. And over here, we're going to divide the right side by the sine of A. That's going to leave us over here with just B. And on the right-hand side, we have A times the sine of B over the sine of A. Okay? Well, now we're going to, this is a good expression for B, okay? That's not really what we're interested in right now. We're developing the sine law, which you'll understand in a second. But now I'm going to do something else. I'm going to divide both sides by the sine of B, okay? And all that's going to do is it's going to move it out of the numerator here, because it's going to divide by something in the bottom here. Maybe I'll just write it. So we're going to divide by the sine of B. And over here, we're going to divide by the sine of B. So here, our sine of B in the top and the bottom, in the numerator and denominator, cancel out. And on the left-hand side, we're left with B over the sine of B is equal to A over the sine of A. Can someone please tell me what these little lowercase letters represent? Side lengths. And these capital letters?
The vertices.
Yep, good. Angles. So if we have a side length and its opposite angle, we have a complete ratio, comparison of numbers, and it is equal to the ratio that we have with any other side length and its opposite angle. What do you think about this? Is this going to be true?
Yes.
That is going to be true as well. Because we could have started this with, you know, the side length, the other side length in here. This, ignore it. I'm not talking about this C right now, although I guess I am actually. Because you could have split this triangle going this way with this altitude, and then you'd have 2 right angle triangles, and you do the same exercise, and you'd end up with an expression for C that equals one of these 2 expressions. And so this is the sine law right here, okay? We can repeat this process for any other altitude in any other triangle, and it will come out telling us that the relationship between the side length and the sine of its opposite angle is equal for every side length and the sine of its opposite angle. Now, why is this helpful? Now, if we look at any triangle in the whole world, any acute triangle, I should say, and you have, let's say, 3 pieces of this information. You have A, side A, and angle A, and then you have any other side, you can find out the other angle. And if you have 2 of the angles, you can find the 3rd angle. And if you have all the angles, you can easily find the last side. Okay, so this is a tool that's going to get us to that point that if we have enough information to use it, if we have what I call opposite information, like if I have A, angle A, and side A, then I can use sine law in order to solve it because I'll have one complete ratio. At any rate, if you have a little bit of space left at the bottom of that page, I'm just going to write a definition for the sine law, and then we'll carry on to some examples. Am I good to erase this? Okay, so sine law. What is it? The relationship between the sides and their opposite angles a relationship between the sides and their opposite angles in any acute triangle. And we'll call it this triangle ABC. In any acute triangle ABC. So that's what it does. That's what it does. It relates the sides and opposite angles. Here's the law. A over the sine of A equals lowercase b over the sine of capital B equals lowercase c over the sine of capital C. And I'll draw a triangle. Make sure it looks like it's not a right angle triangle because that would be confusing. I'm going to call it A, B, C. Name the side lengths A, B, C. And that gives you something to envision and think about. So if you have B and B, we call that opposite information. That means you have the side length and its opposite angle. Then you can create this ratio, which means that if you then have any other piece of information in the triangle, you can use this to solve for some unknown piece of information. Does that make sense? So if I have A, I can solve for A. If I have angle C, I can solve for side length C, or vice versa. Okay? There's one other way to write this equation to use the sine law. If you're trying to find a side length, then this is a good way to use it. If you're trying to find an angle, then you can also write it like this. You could put the sine of the angle in the top. You're just inverting each fraction. So this statement is also true. Now, when you're using this, you'll never actually need all three parts to use it. You only need two parts at a time. Two ratios equal to each other sets up a proportion, which you can use to solve problems. Okay, so you'll never actually have all three of these parts lined up. It's just showing you that you can use any of the three parts. Okay, you can use two of them. You can relate A's and C's, or you can relate C's and B's, or you can relate B's and A's. If you're solving for a side length, you're going to want to use this one because it's easier to multiply both sides by the bottom in order to isolate the variable on top. If you're looking for an angle, probably going to use this one. It's just easier, one step easier. Okay, let's take that sine law and apply it in example 1. You have a diagram there. I'm going to draw a simplified diagram on my board that you can also use. It's always good to add a diagram, especially if you're not sure what's going on, or maybe they don't give you a diagram. Helps you think about it. And again, this strategy is going to work in any acute triangle. That means a triangle in which all of the angles are less than 90 degrees. So here we have example 1. We're going to find a side length using the sine law. So a bicycle path forms a 66-degree angle with one lock of a canal. At a distance of 2.5 kilometers along the path, the angle separating this lock from the next lock is 52 degrees. How far apart are the two locks? So here we go. Here's my diagram. There's the canal. We've got lock 1, bike path, angle to lock 2, 52 degrees here, 66 degrees here, and we know you've traveled 2.5 kilometers along that bike path. Okay, you notice I don't have a right angle here, so I can't use my primary trig ratios, SOHCAHTOA. I have to use another tool. So we're going to apply the sine law. Let's give this some letters so that we can actually talk about it. Let's call that L, let's call that K, and let's call that capital P. Again, it does not matter what you call your vertices. If the diagram gives them names already, then use those. Otherwise, you have the opportunity to name them whatever you like. Okay, what's the goal of this? We want to know how far apart the locks are. So we're looking for the length of LK. Because the opposite angle is called capital P, I'm going to give it the name of lowercase p. And that's what we're solving for. I'm going to write my sine law at the top of every page. So I've got A over sine A equals B over sine B equals C over sine C. And then you're going to say, but Mr. V, there are no A, B's, or C's in this triangle. Letters are just letters. You can use, as long as you have matching information or opposite information, that's the key, right? So I know we're looking for side length P. We don't know it, but that's what I'm going to end up putting in the top. Now, we're also missing, I don't actually have enough information to use this law, do I? I have angle P, but I don't have side P. I have angle L, but I don't have side L. And I have side K, but I don't have angle K.
You can get angle K because you know that any triangle equals 180 in the angle.
So step one here is going to be find angle K. Angle K is 180 degrees minus, in brackets, 66 plus 52. That's going to tell me that angle K measures 62 degrees. Okay, I can add that to my diagram. And now I do have opposite information, don't I?
Yeah.
I have angle K and side K, which means I can set up my sine ratio. I'm looking for side length P, so that means P and P are going to be involved in my equation as well. So I'm going to set it up like this, and this is the easiest way to set it up. You can watch and it'll help you. Here we go. The unknown is going to go in the top. Okay, side length P is going to go in the top, and it's going to go in my first ratio. And underneath here is going to go the sine of angle P. And then it's going to be equal to the ratio that I do know, the one that I have completed. That's going to be side length K over the sine of angle K. You're saying, Mr. V, you don't have a side length K in your diagram. Yeah, I do. The side length is always named after its opposite angle. So even though it doesn't say K up here, you know I'm talking about that side length because it's opposite angle K. Okay, plug in what I know. I don't know lowercase p. I know angle P is 52. So in the bottom there, in the denominator of my first ratio, I have the sine of 52. And in my second ratio, I do have the numerator. K is 2.5. And the denominator is going to be the sine of angle K, which is 62 degrees. We found that out up here. How do I solve for P? Right now it's being divided by the sine of 52. Good, so I'm going to multiply both sides by the sine of 52 degrees. Multiply both sides by the sine of 52 degrees. Over here, that's going to leave me with just P. On the right-hand side, I'm going to have in the numerator 2.5 times the sine of 52 over the sine of 62 degrees. And I'm going to carefully punch that into my calculator and try to show you what happens here and how I do it. You could do it all in one sentence. I don't typically do these ones all in one go. I typically go 2.5 sine 52. Don't have to put in any brackets. If you do it this way, your calculator can do this really easily. It knows just what to do. It's going to take the sine of 52 and then it's going to multiply it by 2.5. I hit enter. I leave that in my screen. I don't write anything on my paper. I just leave that in my screen and then I hit divided by the sine of 62. Again, you don't need to put any brackets and you hit enter and you end up with 2.231. So we're going to round that to P is approximately 2.2. We're measuring in kilometers. So the distance between the two locks is approximately 2.2 kilometers. We were to round to the nearest tenth of a kilometer, so there you go. The distance between the locks is 2.2 kilometers. Sure. Approx. Okay, that's using sine law. What did we need? We needed opposite information. In this example, we didn't have it. At least it looked like we didn't have it, so we needed to use our sum of interior angles to first get that one completed ratio, and then we could use it to work through the rest of the problem. All right, example 2. Example 2 is going to be very similar. This time we are using the sine law in order to find a missing angle. So that's why we rewrote the sine law in 2 different ways. This time, since we're looking for a missing angle, I'm going to be thinking about using it inverted. And I'm going to be aware of the fact that the sine of an angle over its opposite side length is going to create my ratio. That's just going to allow me to not be solving for something in the denominator. It's much easier to solve for something in the numerator than it is to solve for something in the denominator. All right, we've got triangle here, and they don't give you a diagram. So we're going to be drawing our own diagram, and we're going to think about how to do that. I'm going to tell you the easiest way to do that, and then you can use that strategy in the rest of your efforts, okay? So in acute triangle TUV, we're given the measurement of TU, we're given the measurement of UV, and we're given the measurement of angle T. We need to find the measure of angle V to the nearest degree. Now, I don't know how good you are with abstract mental imaging, but I can't picture this triangle. Okay, I don't know what I'm looking for, what's there, what's not there, unless I draw it. So I'm going to draw it, and here's how you draw it. You're always going to start with a horizontal line. Okay? It doesn't even matter how long you make that horizontal line. You can adjust it as you go. The reason you start with a horizontal line is because you're actually going to start with the angle that they give you. You're going to measure angle T. So you're just going to try to draw something like a 31-degree angle. And you're going to call it vertex T. Then you're going to go back and look at what else they've given you, okay? They've given you the measurement of TU and the measurement of UV. So now it doesn't really matter whether you call this TU or this side length TU, but because I have been given angle T and it's easier for me to think across here, I'm just going to put a dot here. I'm going to call that U. And I know that that is 11.1 centimeters. The other piece of information that they give you is that UV, so we don't know where V is, it's going to be somewhere along this line. If UV was really, really long, like longer than 11, then I would know it kind of goes off this way. But they tell us that UV is 5.8. So it's just bigger than half of this line. So it makes sense that it's pretty short. So it's actually going to come something like this. Okay? And again, your diagrams don't necessarily need to be perfect, but they could be pretty close to perfect. And I had a little extra tail on here that I now don't need, so I just erase it. And now I have triangle TUV, and I have all my measurements that they've given me. Okay, again, start with a horizontal line and draw your angle.
It's great to learn this on Unit 8.
Leave those lengths as long as you need to, and then go for it from there. Well, you've never drawn difficult triangles before, right? Drawing a right angle triangle is easy. Drawing a right angle triangle, you start with your right angle and go from there. But if you don't know what the triangle looks like, you start with the angle that they give you and a side length that they give you from that angle and go from there. Okay, so we've drawn it, and now we're going to simply apply the sine law, and we are looking for angle V. So we're looking for this right here, which means this 11.1 is going to come into play. And do we have enough information to use the sine law?
Yes.
Yeah, I've got opposite information right here to create my first ratio. So let's do it. We're going to set it up. We're looking for angle V, so I'm going to put the sine of V in my numerator. It's going to be over the side length V. And then the known information is T and T. So I've got in the numerator the sine of angle T over the side length T. Now I can plug in what I know. You don't always need to write this, okay? If you're getting good at this and you don't need this, then you just plug in your information right away. The numerator I don't know anything about, so I leave v there. That's what I'm trying to find out. The length v is 11.1. Then with my t's, in the numerator, the sine of angle t, they gave me that in the word problem. That's 31 degrees. That's going to be over the side length t, which is right here. It's the line segment UV. It's 5.8. All right, how do I isolate v? Can I isolate v directly?
No.
I can isolate the sine of v. So that's our next step. We're going to get sine v by itself by doing what? Multiply both sides by 11.1. On the left, that leaves us with the sine of capital V. On the right, watch what I do with this. I know that multiplying by 11.1, it's kind of like 11.1 over 1. It just bumps this 11.1 into the numerator. And the easiest way to think about that in your calculator is going to be 11.1 times the sine of 31. It's going to be all over 5.8. Lots of different ways you can put this in your calculator. And that's what we're going to do next. But you could do 11.1 divided by 5.8, then times sine 31, if you hit enter here. Or you can do 11.1 sine 31, enter, divide by 5.8. You probably could even do just 11.1 sine 31, divide by 5.8, all in one go. That would probably work out just nicely. So let's carefully get our calculators going here. By the way, when I do this, is this going to give me the angle measurement?
No.
No, it's going to give me the sine ratio. It's going to give me the sine ratio of angle V. We're actually looking for angle V. But first things first, here we go. 11.1 sine 31. Close that bracket, the little one right there at the end of the 31. Divide by 5.8, enter. I get 0.985676316. Now I'm looking at this, I'm saying, oh, that's not an angle. That's a weird, that'd be a tiny little angle, and it's actually quite a large angle. It's pretty close to 90 degrees. Yeah, so I actually need to just leave this answer in there. I'm not even going to do this. This is what you might be tempted to do. You're going to write the sine of v equals 0.986. I'll just round it. And then you're going to take the inverse sine of that. You're going to get a rounded answer using a rounded value. That's not a good idea. So your calculator will just keep that accurate answer saved, and all you need to do is hit second function sine. That gives you the inverse sine. Then you're going to hit second function answer. That's going to give you that stored answer. And you end up with the angle measurement V equals 80.3 degrees. Okay? So that little answer button is down here. Second function, negative. Right above that, little letters ANS. That means it's going to input the last stored answer, the last stored calculation. Okay? If you did it in 2 steps and you rounded this to like 4 or 5 decimal places, that's fairly safe to do, but you don't need to do it. It's much more accurate if you don't.
What did you do?
And we're actually asked to get v to the nearest degree. So, and this is approximate, by the way. You can put a dot above there. So you can do the measure of angle v is approximately 80 degrees. Okay? Now, we weren't asked to solve this whole triangle, but now we have 2 of the angles. How would I get the third angle? Would I have to do sine law again?
No.
No. What would I do?
You would just subtract 80 and 31 from 180.
Good. I'd just use sum of interior angles, and I'd get this angle. Now, how would I get this side length?
I forgot.
Can I use Pythagorean theorem?
Yes.
No.
No.
Why not?
Oh, it's not a right
It's
angle.
not a right angle triangle.
Oh.
Can I use primary trig ratios? SOHCAHTOA? No. Why not?
It's not a right.
Not a right angle triangle. Can I use sine law?
Yeah.
Of course. I have opposite information, and I just found the angle. So I'd be flipping this around, inverting my sine law. in order to solve for side length u. Okay? All right, example 3. Example 3, we're heading to Bermuda Triangle, and we're asked to find the perimeter of the Bermuda Triangle to the nearest 100 kilometers. Do you have a picture in your notebook? Okay, I'm going to draw a little bit of a simplified diagram here. We've got M, B, S. We're told that the angle from M, the angle between B and S, is 50 degrees. And we're told that from S, the angle between M and B is 74 degrees. And we're given a side length. We're given 1,000 kilometers from M to S. And we need the perimeter. So what's our goal here? What are we gonna try? Oh, it's 1,600, not 1,000. Couldn't see that in my diagram. 1,600. What do we need if we're finding perimeter?
We need all the outside lengths of the sides. Lengths of the sides.
Yeah, we need side lengths. So we're gonna end up being MB plus BS or SB and plus SM. That's our goal. That'll give us the perimeter. We already have one of those. We have MS. Do I have enough information to find side length M here? Or BS, I'll just call it. No, I don't. And what about MB?
No.
Nope. I have one more step to do. What do I need to do?
You need to take 180 and back by the addition of 50 plus.
Yeah, first I need to find angle B here. So I'm going to take angle B. It's going to equal 180 minus, and again, you can write it two different ways. I normally add up the other ones in brackets, but you could also just write this, minus 50, minus 74. I don't know why I don't like that one more. It is easier in the calculator anyway. And that equals 56 degrees. Now do I have opposite information?
Yes.
Yes, which means I can apply the
sine law.
sine law. What would you like to solve for first? Side length M or side length S?
Side length.
It doesn't matter at all, not even a little bit. Okay, sure, let's solve for side length S. So we have side length S, we're going to go with lowercase s on top over the sine of angle S. That's going to be equal to our other ratio, which I'm going to use my completed ratio. It's going to be side length B over the sine of capital B. Okay, plug in what I know. I don't know side length S. I do know the angle S is 74 degrees. I know side length B is 1,600 over angle B, which is going to be the sine in the denominator. We're going to have the sine of 56 degrees. How do I solve for S? Multiply both sides by the sine of 74, not by 74. It's going to end up looking like this. S equals, in the numerator, 1,600 sine 74. Okay, you don't even need brackets or anything, and that still makes perfect sense. This is a single entity. It is a ratio comparing sides in a right angle triangle. Okay, you say we don't have a right angle triangle, that's okay. But that's what it is. It's a sine ratio. And then in the numerator, or the denominator, sorry, we still have sine of 56. Which tells us that the side length S, carefully in our calculator, is approximately 1855. That's going to be measured in kilometers. How do I get the other missing side length? How do I get the other missing side length?
By using the other thing.
Yeah, I have to use sine law again. Okay, I can't use Pythagorean theorem. It's not a right angle triangle. I have to use sine law again. And this time I'm going to still use my ratio right here of 1,600 over the sine of 56. But this time it's going to be equal to, because we're looking for side length M. So our first ratio is going to be M over the sine of 50 degrees. That's angle M. Notice I'm skipping this little portion where I just write the formula that I'm using. And our completed ratio over here is going to be same. It's going to be 1,600 over the sine of 56. Now, could I, quick question, I did already find that side length S is 1855. Could I use this as my opposite information to set up the other ratio?
Yes.
Yeah, I could. Why am I not doing that?
Because it's 18.
I could have made a mistake, okay? And I don't want to use information that I've calculated when I could easily use information that they've given for free, okay? So what do I do here to solve for M? Multiply both sides by the sine of 50. Carefully type that into your calculator. You'll get that the length of side M is approximately 1478. And now what do I do? Am I done?
You add them all up.
Yeah, I'm not looking for each individual side length. I'm looking for the perimeter. So perimeter equals 1600 plus 1855 plus 1478. Put it in your calculator. That's going to be 4933 kilometers. The perimeter of the Bermuda Triangle is about 4933 kilometers. Go ahead and sail it.
Yeah.
All right, what did we do? We used one new tool, Sine Law. Okay, it's not the Sine Ratio. That's primary trig ratios only in right angle triangles. This is the Sine Law. It relates a side and its opposite angle in an acute triangle, creating a ratio. If you have opposite information, then you use other bits and pieces to set up a proportion. You solve for the missing information, and you can get the rest of the information from the triangle that way as well. Don't forget about the sum of interior angles. If you're missing an angle, that might help you along the way. And again, like this one, we used Sine Law twice in one problem. Okay, no big deal. Your practice problems for 8.1 are from page 366, numbers 1 through 6, and number 10. Thanks for coming.